Chapter 4, Part 1 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 1. Progress of Astronomy during the first half of the 19th century. Chapter 4. Planetary Discoveries. Part 1. In the course of his early gropings towards a law of the planetary distances, Kepler tried the experiment of setting a planet, invisible by reason of its smallness, to revolve in the vast region of seemingly desert space separating Mars from Jupiter. The disproportionate magnitude of the same interval was explained by Kant as due to the overweening size of Jupiter. The zone in which each planet moved was, according to the philosopher of Königsberg, to be regarded as the empty storehouse from which its materials had been derived. A definite relation should thus exist between the planetary masses and the planetary intervals. Lambert, on the other hand, sportively suggested that the body or bodies, for it's noticeable that he speaks of them in the plural, which once bridged this portentous gap in the solar system, might, in some remote age, have been swept away by a great comet and forced to attend its wanderings through space. These speculations were destined before long to assume a more definite form. Johann Daniel Titius, a professor at Wittenberg, where he died in 1796, pointed out in 1772, in a note to a translation of Bonnet's Contemplation de la Nature, the existence of a remarkable symmetry in the disposition of the bodies constituting the solar system. By a certain series of numbers, increasing in irregular progression, he showed that the distances of the 6 known planets from the Sun might be represented with a close approach to accuracy, but with one striking interruption. The term of the series succeeding that which corresponded to the orbit of Mars was without a celestial representative. The orderly flow of the sequence was thus singularly broken. The space where a planet should, in fulfillment of the law, have revolved was, it appeared, untenanted. Johann Elert Bode, then just about to begin his long career as leader of astronomical thought and work at Berlin, marked at once the anomaly and filled the vacant interval with a hypothetical planet. The discovery of Uranus at a distance falling but slightly short of perfect conformity with the law of Titus lent weight to a seemingly hazardous prediction, and von Zach was actually at the pains in 1785 to calculate what he termed analogical elements for this unseen and, by any effect or influence, unfelt body. The search for it, through confessedly scarcely less chimerical than that of alchemists for the philosopher's stone. He kept steadily in view for 15 years, and at length, September 21, 1800, succeeded in organizing, in combination with 5 other German astronomers assembled at Lilienthal, a force of what he jocularly termed celestial police, for the express purpose of tracking and intercepting the fugitive subject of the sun. The zodiac was accordingly divided for purposes of scrutiny into 24 zones. Their apportionment to separate observers was in part effected, and the association was rapidly getting into working order, when news arrived that the missing planet had been found. Through no systematic plan of search, but by the diligent, though otherwise directed, labors of a distant watcher of the skies. Giuseppe Piazzi was born at Ponte in the Valtelline, July 16, 1746. He studied at various places and times under Teraboschi, Beccaria, Jacqueur, and Lissur, and having entered the 13th order of monks at the age of 18, he taught philosophy, science, and theology in several of the Italian cities, as well as in Malta, until 1780, when the chair of mathematics in the University of Palermo was offered to and accepted by him. Prince Caramanico, then Viceroy of Sicily, had scientific learnings, and was easily won over to the project of building an observatory, a commodious foundation for which was afforded by one of the towers of the viceregal palace. This architecturally incongruous addition to an ancient Saracenic edifice, once the abode of Chalybeate and Zirid emirs, was completed in February 1791. Piazzi, meanwhile, had devoted nearly 3 years to the assiduous study of his new profession, acquiring a practical knowledge of Lalande's method at the École Militaire and of Maskelyne's at the Royal Observatory, and returned to Palermo in 1789, bringing with him, in the great 5-foot circle which he had prevailed upon Ramsden to construct, the most perfect measuring instrument hitherto employed by an astronomer. He had been above 9 years at work on his star catalogue, and was still profoundly unconscious that a place amongst the Lilienthal band of astronomical detectives was being held in reserve for him when, on the first evening of the 19th century, January 1, 1801, he noticed the position of an 8th magnitude star in a part of the constellation Taurus, to which an arrow of Wollaston's had directed his special attention. Reobserving, according to his custom, the same set of 50 stars on 4 consecutive nights, it seemed to him on the second that the one in question had slightly shifted its position to the west. On the third, he assured himself of the fact, and believed that he had chanced upon a new kind of comet without tail or coma. The wandering body, whatever its nature, exchanged retrograde for direct motion on January 14, and was carefully watched by Piazzi until February 11, when a dangerous illness interrupted his observations. He had, however, not omitted to give notice of his discovery, but so precarious were communications in those unpeaceful times that his letter to Oriani of January 23 did not reach Milan until April 5, while a missive of 1 day later, addressed to both, came to hand at Berlin, March 20. The delay just afforded time for the publication by a young philosopher of Jena named Hegel of a dissertation showing, by the clearest light of reason, that the number of the planets could not exceed 7, and exposing the folly of certain devotees of induction who sought a new celestial body merely to fill a gap in a numerical series. Unabashed by speculative scorn, Bode had scarcely read Piazzi's letter when he concluded that it referred to the precise body in question. The news spread rapidly and created a profound sensation, not unmixed with alarm, lest this latest addition to the solar family should have been found only to be again lost. For by that time Piazzi's moving star was too near the sun to be any longer visible, and in order to rediscover it, after conjunction, a tolerably accurate knowledge of its path was indispensable. But a planetary orbit had never before been calculated from such scanty data as Piazzi's observation afforded, and the attempts made by nearly every astronomer of note in Germany to compass the problem were manifestly inadequate, failing even to account for the positions in which the body had been actually seen, and, a fortiori, serving only to mislead as to the places where, from September 1801, it ought once more to have become discernible. It was in this extremity that the celebrated mathematician Gauss came to the rescue. He was then in his 25th year, and was earning his bread by tuition at Brunswick, with many possibilities, but no settled career before him. The news from Palermo may be said to have converted him from an arithmetician into an astronomer. He was already in possession of a new and more general method of computing elliptical orbits, and the system of least squares, which he had devised, though not published, enabled him to extract the most probable result from a given set of observations. Armed with these novel powers, he set to work, and the communication in November of his elements and ephemeris for the lost object revived the drooping hopes of the little band of eager searchers. Their patience, however, was to be still further tried. Clouds, mist, and sleet seemed to have conspired to cover the retreat of the fugitive. But on the last night of the year the sky cleared unexpectedly, with the setting in of a hard frost, and there, in the northwestern part of Virgo, nearly in the position assigned by Gauss to the runaway planet, a strange star was discerned by von Zach at Gotha, and on a subsequent evening, the anniversary of the original discovery, by Olbers at Bremen. The name of Ceres, as the tutelary goddess of Sicily, was, by Piazzi's request, bestowed upon this first known of the numerous and probably all but innumerable family of the minor planets. The recognition of the second followed as the immediate consequence of the detection of the first. Olbers had made himself so familiar with the positions of the small stars along the track of the long missing body that he was at once struck, March 28, 1802, with the presence of an intruder near the spot where he had recently identified Ceres. He at first believed the newcomer to be a variable star, usually inconspicuous, but just then at its maximum of brightness. But within 2 hours he had convinced himself that it was no fixed star, but a rapidly moving object. The aid of Gauss was again invoked, and his prompt calculations showed that this fresh celestial acquaintance, named Pallas by Olbers, revolved around the sun at nearly the same mean distance as Ceres, and was beyond question of a strictly analogous character. This result was perplexing in the extreme. The symmetry and simplicity of the planetary scheme appeared fatally compromised by the admission of many, where room could, according to old-fashioned rules, only be found for one. A daring hypothesis of Olbers' invention provided an exit from the difficulty. He supposed that both Ceres and Pallas were fragments of a primitive trans-Martian planet blown to pieces in the remote past, either by the action of internal forces or by the impact of a comet, and predicted that many more such fragments would be found to circulate in the same region. He moreover pointed out that these numerous orbits, however much they might differ in other respects, must all have a common line of intersection, and that the bodies moving in them must consequently pass, at each revolution, through two opposite points of the heavens, one situated in the Whale, the other in the constellation of the Virgin, where already Pallas had been found and Ceres recaptured. The intimation that fresh discoveries might be expected in those particular regions was singularly justified by the detection of two bodies, now known respectively as Juno and Vesta. The first was found near the predicted spot in Sirius by Harding, Schroeder's assistant at Lilienthal, September 2, 1804. The second by Olbers himself in Virgo, after 3 years of persistent scrutiny, March 29, 1807. The theory of an exploded planet now seemed to have everything in its favor. It required that the mean or average distances of the newly discovered bodies should be nearly the same, but admitted a wide range of variety in the shapes and positions of their orbits, provided always that they preserved common points of intersection. These conditions were fulfilled with a striking approach to exactness. 3 of the 4 asteroids, a designation introduced by Sir W. Herschel, conformed with very approximate precision to Baude's law of distances. They all traversed in their circuit round the sun nearly the same parts of Sirius and Virgo, while the eccentricities and inclinations of their path departed widely from the planetary type, that of Pallas, to take an extreme instance, making with the ecliptic an angle of nearly 35 degrees. The minuteness of these bodies appeared further to strengthen the imputation of a fragmentary character. Herschel estimated the diameter of Ceres at 162, that of Pallas at 147 miles, but these values are now known to be considerably too small. A suspected variability of brightness in some of the asteroids, somewhat hazardously explained as due to the irregularities of figure to be expected in cosmical potsherds, so to speak, was added to the confirmatory evidence. The strong point of the theory, however, lay not in what it explained, but in what it had predicted. It had been twice confirmed by actual exploration of the skies, and had produced in the recognition of Vesta the first recorded instance of the premeditated discovery of a heavenly body. The view not only commended itself to the facile imagination of the unlearned, but received the sanction of the highest scientific authority. The great Lagrange bestowed upon it his analytical imprimatur, showing that the explosive forces required to produce the supposed catastrophe came well with the bounds of possibility, since a velocity of less than 20 times that of a cannonball leaving the gun's mouth would have sufficed, according to his calculation, to launch the asteroidal fragments on their respective path. Indeed, he was disposed to regard the hypothesis of disruption as more generally available than its author had designed it to be, and proposed to supplement with it as explanatory of the eccentric orbits of comets the nebular theory of Laplace, thereby obtaining, as he said, a complete view of the origin of the planetary system more conformable to nature and mechanical laws than any yet proposed. Nevertheless, the hypothesis of Olbers has not held its ground. It seemed as if all the evidence available for its support had been produced at once and spontaneously, while the unfavorable items were elicited slowly and as it were by cross-examination. A more extended acquaintance with the group of bodies, whose peculiarities it was framed to explain, has shown them, after all, as recalcitrant to any such explanation. Coincidences, at the first view significant and striking, have been swamped by contrary examples, and a hasty general conclusion has, by a not uncommon destiny, at last perished under the accumulation of particulars. Moreover, as has been remarked by Professor Newcomb, mutual perturbations would rapidly efface all traces of a common disruptive origin, and the catastrophe, to be perceptible in its effects, should have been comparatively recent. A new generation of astronomers had arisen before any additions were made to the little family of the minor planets. Piazzi died in 1826, Harding in 1834, Olbers in 1840. All those who had prepared or participated in the first discoveries passed away without witnessing their resumption. In 1830, however, a certain Henke, ex-postmaster in the Prussian town of Dresden, set himself to watch for new planets, and after 15 long years his patience was rewarded. The asteroid found by him December 8, 1845, received the name of Astrea, and his further prosecution of the search resulted, July 1, 1847, in the discovery of Hebe. A few weeks later, August 13, John Russell Hind, 1823 to 1893, after many months' exploration from Mr. Bishop's observatory in the Regent's Park, picked up Iris, and October 18, Flora. The next on the list was Metis, found by Mr. Graham, April 25, 1848, at Markry in Ireland. At the close of the period to which our attention is at present limited, the number of these small bodies known to astronomy was 13, and the course of discovery has since proceeded far more rapidly and with less interruption. Both in itself and in its consequences, the recognition of the minor planets was of the highest importance to science. The traditional ideas regarding the constitution of the solar system were enlarged by the admission of a new class of bodies, strongly contrasted yet strictly coordinate with the old established planetary order. The profusion of resource, so conspicuous in the living kingdom of nature, was seen to prevail no less in the celestial spaces, and some faint preliminary notion was afforded of the indefinite complexity of relations underlying the apparent simplicity of the majestic scheme to which our world belongs. Both theoretical and practical astronomy derived profit from the admission of these apparently insignificant strangers to the rights of citizenship of the solar system. The disturbance of their motions by their giant neighbors afforded a more accurate knowledge of the Jovian mass, which Laplace had taken about 1/5 too small. The anomalous character of their orbits presented geometers with highly stimulating problems in the theory of perturbation, while the exigencies of the first discovery had produced the theoria motus, and won Gauss over to the ranks of calculating astronomy. Moreover, the sure prospect of further detections powerfully incited to the exploration of the skies. Observers became more numerous and more zealous in view of the prizes held out to them. Star maps were diligently constructed, and the sidereal multitude strewn along the great zodiacal belt acquired a fresh interest when it was perceived that its least conspicuous member might be a planetary shred or projectile in the dignified disguise of a distant sun. Harding's Celestial Atlas, designed for the special purpose of facilitating asteroidal research, was the first systematic attempt to represent to the eye the telescopic aspect of the heavens. It was, while engaged on its construction, that the Lilienthal observer successfully intercepted Juno on her passage through the Veil in 1804. Whereupon, promoted to Göttingen, he there completed in 1822 the arduous task so opportunely entered upon a score of years previously. Still more important were the great star maps of the Berlin Academy, undertaken at Bessel's suggestion, with the same object of distinguishing errant from fixed stars, and executed under Encke's supervision during the years 1830 to 59. They have played a noteworthy part in the history of planetary discovery, nor of the minor kind alone. We have now to recount an event unique in scientific history. The discovery of Neptune has been characterized as the result of a movement of the age, and with some justice. It had become necessary to the integrity of planetary theory. Until it was accomplished, the phantom of an unexplained anomaly in the orderly movements of the solar system must have continued to haunt astronomical consciousness. Moreover, it was prepared by many, suggested as possible by not a few, and actually achieved simultaneously, independently, and completely by two investigators. The position of the planet Uranus was recorded as that of a fixed star no less than 20 times between 1690 and the epoch of its final detection by Herschel. But these early observations, far from affording the expected facilities for the calculation of its orbit, proved a source of grievous perplexity. The utmost ingenuity of geometers failed to combine them satisfactorily with the later Uranian places, and it became evident either that they were widely erroneous, or that the revolving body was wandering from its ancient track. The simplest course was to reject them altogether, and this was done in the new tables published in 1821 by Alexis Bouvard, the indefatigable computating partner of Laplace. But the trouble was not thus to be got rid of. After a few years, fresh irregularities began to appear, and continued to increase until absolutely intolerable. It may be stated as illustrative of the perfection to which astronomy had been brought, that divergences regarded as menacing the very foundation of its theories never entered the range of unaided vision. In other words, if the theoretical and the real Uranus had been placed side by side in the sky, they would have seemed to the sharpest eye to form a single body. The idea that these enigmatical disturbances were due to the attraction of an unknown exterior body was a tolerably obvious one, and we accordingly find it suggested in many different quarters. Bouvard himself was perhaps the first to conceive it. He kept the possibility continually in view, and bequeathed to his nephew's diligence the inquiry into its reality when he felt that his own span was drawing to a close. But before any progress had been made with it, he had already, June 7th, 1843, ceased to breathe and to calculate. The Rev. T.G. Hussey actually entertained in 1834 the notion, but found his powers inadequate to the task of assigning an approximate place to the disturbing body, and Bessel in 1840 laid his plans for an assault in form upon the Uranian difficulty, the triumphant exit from which fatal illness frustrated his hopes of effecting or even witnessing. the problem was practically untouched when, in 1841, an undergraduate of St. John's College, Cambridge, formed the resolution of grappling with it. The projected task was an arduous one. There were no guiding precedents for its conduct. Analytical obstacles had to be encountered so formidable as to appear invincible even to such a mathematician as Airy. John Couch Adams, however, had no sooner taken his degree, which he did as senior wrangler in January 1843, than he set resolutely to work, and on October 21st, 1845, was able to communicate to the Astronomer Royal numerical estimates of the elements and mass of the unknown planet, together with an indication of its actual place in the heavens. These results, it has been well said, gave the final and inexorable proof of the validity of Newton's law. The date October 1st, 1845, may therefore be regarded as marking a distinct epoch in the history of gravitational astronomy. End of chapter 4, part 1.